So last time we did this analysis of this problem using more features, basically. So we did for an estimate of the optimal classifier for the case where we use the two features in the Titanic data set. And we came up with this decision tree type summarization. And this simplified to this decision tree. And then we did a calculation with the actual data that we'll try to verify in your homework problem. And we got that with this data, the training error is 0.219 or 219, and the other number is the test error 0.211. And for the classifier that did not take into account the P class, so basically the one that ignores this split here, so just does this or that, decides based on those. The training error turns out to be that, and then the test error turns out to be this. So comparing the test errors, let's say, we see that the classifier that uses both covariates or both features seems to do a little bit better. And then the question was whether we have or we want to go with this or not, right? So do we want to use this more complex example or like more complex classifier or not? So we went through this discussion, and one of you, I guess, Olivia, which I don't, yeah, she's here. So she suggested that maybe the difference is not much, and maybe we should go with the simpler classifier, right? And this is a good, like, let's say, statistical instinct. So statisticians worry about like small differences. Does it matter? Does it not matter? And then they also worry about simplicity or interpretability. So the model that just uses this one feature is more simple. So you might want to use that if you're biased towards more simple models. And we mentioned that from a decision theoretic perspective, our cost is only the risk or the, in this case, misclassification rate or the generalization error. So if we set out that as our goal, then the simplicity or complexity doesn't matter. If we want to include that, we could like add it as a penalty to the risk, let's say, if you want. Or like it's an extra consideration that we have to somehow accommodate. So if we had the actual generalization error, and the actual generalization error or the risk was like this, then we would go within the framework that we said, we would go with the more complex model here. But the issue here is this is not the actual risk. And you're using, it turns out, I think, the sample size 327, something like that, for our test data. So this is an estimate of the generalization error. We know that if the sample size grows, it's going to be a consistent estimate. It's going to approach the true generalization error. But right now, we have 300 or so. It's not infinite, right? So can we do some sort of a statistical analysis or like a statistical test to test whether at this level, given this sample size, can we say that this is better than that? So what do you guys think? Do you know how to like have an idea how to perform a test, like statistical test? It's good to do this because we're teaching this in the stat department. It's good to do at least one like hypothesis test to make sure that we paid our dues to the stat department. Right? So how should we proceed? Have you seen something like this or thought about this? from last lecture to this lecture. So let me help you a little bit. So what is the test error? The test error is a quantity like this, right? And if you remember, we're taking these independent sample or like samples or examples. And for computing the test error, you can basically treat f hat, the estimator that you're evaluating, as constant, or you can condition on your training. So this is a constant function, and I'm evaluating it at x tilde I and comparing it to y tilde I. This is going to be a binary variable, okay? And as I vary I, these are going to be independent binary variables because the test is designed like that. So you're assuming that each one of these is an IID draw from the actual distribution. And so these are, in the language of probability theory, these are Bernoulli variables, okay? Bernoulli distributed variables, right? So I have something like, if I call this ZI, the test error is an average of these Bernoulli variables, and the Bernoulli variables are IID. Again, everything is conditional on the training. They're IID Bernoulli with some probability. Anyone knows what that probability is? What is the probability that each one is 1? What do we call it? Think of f hat as fixed, deterministic. What is the probability that Zi is 1? It has a name. It's one of the things that we're after. A certain like error or yes.
Is it just the misclassification rate?
It's the misclassification rate, or I'm going to say it's just the risk, right? It's just the probability that like an unseen example, we make an error on it. So it's like probability of, remember this for a fixed f, something like this is the risk, misclassification rate, right? So this is the probability. The probability of this coming up 1 is just the risk that you're after. So you're basically flipping a coin with the probability of coming up heads being the quantity that you're after, which is just the risk of f hat, right? This is just a number, right? For example, 0.2, 0.22. If you flip a coin, each one is like either 1 or 0, and it's 1 with this probability, right? And you're taking the average, you know that the average sort of converges to this probability by the law of large numbers, right? So we have IID draws Bernoulli with probability, which is the quantity that we want, right? Just imagine, what is the probability that this is 1? It's just the probability that this is not equal to that. This is just the misclassification rate, okay? They have the same probability because these are having the same IID distribution. So the problem is I have Bernoulli sequence of Bernoulli variables with a given probability. Like I can say, for example, I have Zi's Bernoulli with probability P, and I form the average Z bar, let's say M, 1 over N summation I from 1 to N, M. And I want to decide whether this is a good estimate of P. So the expectation would be this P. So it's unbiased for P, and there's a variance. So I want to like measure the variance and quantify that uncertainty. The setting that we are looking at is I actually have this for f hat, and then for like f hat 1 and f hat 2 is another sequence of. So if this is, for example, f hat 1, let's say this for, so this is going to be a good approximation. They're going to converge to R of f hat 1. Then I would have maybe like Wi, these are Bernoulli R of f hat 2. So if I apply it to it f hat 2, I call this thing W2. So let's say indicator that f hat 2 xi not equal to ii. This is going to be Bernoulli with the probability being R of f hat 2, right? And is that still correct? So that then I have W bar, let's say M, which is 1 over M summation W I from 1 to M. So this would be my like R training of f hat 2. This would be R training of f hat 1. So that would be like converging to R of f 2. What I'm just saying is that I'm looking at two sample averages. Each one is an average of a bunch of Bernoullis, but the probabilities are different. One is the risk of f hat 1, the other is the risk of f hat 2. I just want to compare whether these two risks are the same. What I want to test is whether this is equal to that. So are these probabilities the same? Let's call this P1. Or let's call this P2. To be P2. So I have two sequences of Bernoulli variables. One would probably P1, the other would probably P2. I form the averages. These are good estimates of P1 and P2. But I want to test whether P1 is equal to P2. I have two proportions, basically, whether at the population level they're the same or not. Right? This is sort of like a common task in statistics. Is that sort of clear to people? So the task of computing the risk via the training error is just doing this averaging of a bunch of Bernoulli variables. If you do look at the test error, and how good of an estimate you are depends on the variance of the sample size and the variance of this, basically. Right. And then you want to compare these to probabilities, basically, whether this is equal to that or not, or whether P1 is bigger than P2 or not. Right. I want to know this. I don't have this, but I just have the estimate, which is this guy, which is the average. Is this sort of clear? Yes.
Sorry, what exactly? Like their accuracy or
That's the misclassification rate or the risk. Right. I want a true risk, right? I want R of f hat. If R of f hat 1 is really bigger than R of f hat 2, f hat 2 is the complex one. I'm going to pick f hat 2. But I don't have the actual risk. I just have this training risk or training error of f hat 1 and training error of hat 2, which is just a sample average of these Bernoullis with that probability. This is also a sample average of those. And I want to compare. I'm comparing basically these, so that would be like point to forgot what the numbers were. Yeah, 217. That's, for example, for f hat 1. This is going to be 0.211. Maybe P1 and the actual risk is actually 0.2, maybe for both. This would be like a quite good estimate. So 2.21 maybe it's the same for both. We don't know. At this level, we don't know. So I just want to say whether P1 is equal to P2 or not. Okay. Yes.
So when you said that's the risk training which is equal to the mean for C, that
This one, yeah.
So is that basically saying that like the training error is basically approximated from the test?
No, the training error. Oh, sorry. Okay, I made a mistake. Sorry. This should be a test error because we're doing, yeah, correct. This is the test. I'm sorry. We're doing it on the test. Otherwise, this wouldn't be correct. Good. Thank you. Yeah, this is the test error. We're doing it on the test data. Yes, thank you. Not the training. The training wouldn't be like IID. So these wouldn't be IID. We talked about that. It would be dependent. It would be dependent. So if this was a training sample, because f had dependent on it, these indicator variables would be all dependent. So we couldn't say that. Very important point. So these are the tests, the risk, like test error or test risk if you want. And then I'm going to compare them. Okay. Does that make sense? So if you understand this, this is sort of an exercise you can try to assign. So that's an exercise notes that I have. So I have a bunch of like ZIs that are Bernoulli PI and a bunch of SWJ, which are Bernoulli P2. And I'm going to estimate the P1 by P hat 1, which is the average of ZIs, and then P hat 2 by the average of, there's a missing thing here. So that would be 1 over M2. So these are good estimates. Then you can calculate the variance of the difference. So one issue is like in our setting, we have both of them are M, and the actual samples are dependent because they're like these two variables are dependent because they're using the same test example. But we're not going to worry about that, as you'll see. So actually, you have to worry a little bit about that. If they're independent, then if they're independent under the P1 and P2 equal to P, the variance would be the variance of the difference you can calculate. So if these were independent samples, so if ZI is independent of WJ, then you could evaluate this variance and this would be that. And then you can say, oh, maybe roughly, because the averages are roughly Gaussian, right? So by the central law of large, by the central limit theorem, the averages are Gaussian. So if I subtract the mean and then divide by the variance, you would hope that this is close to a Gaussian. Okay, so this is sort of Gaussian. This is sort of Gaussian. So the difference is close to a Gaussian, and this is the actual variance if they're independent, and the mean would be 0 because under the hypothesis that the two are the same. So if I have the hypothesis that they're the same, so expectation of P hat 1 would be P1, expectation of P hat 2 would be P2, so the expectation of the difference would be P1 minus P2, which is 0 under the null hypothesis. So this would be centered around 0. So if you look at this statistic, and if I divide it by this variance, this is going to be approximately distributed like a normal variable, which means 0 and variance 1, sort of. This is by CLT because for large enough, this is not exact, but for large enough, this is going to be normal. This is going to be normal. The difference is going to be sort of normal. And this variance you can calculate, and then I can like approximate. So if I want to approximate the variance, I could. So for example, if you have like P hat 1 plus P hat 2 divided by 2, that would be a good estimate of P hat. For example, okay. Actually, what I'm doing here is let's just assume that the M is equal to so M is equal to M here. So M1 is equal to M1. So this M is actually, so if M1 is equal to M2, this M here is just going to be equal to M, right? And then if I'm under the null, if I average the two, this is going to be a good estimate. It's going to be an unbiased estimate of p as well. So I can plug that in. So I get p hat 1 minus p hat 2 root v of p hat approximately normal. So the key is like, I want to have an estimate of the variance, which is controlled by the sample size. If I have that, then I know how far I am. And and then I can form this. This is going to be still approximately normal. And then form this, compare it with a normal distribution. See if it like falls, like is consistent with normal distribution or not. Does that make sort of sense? Just the numbers here. But let me know if it's not clear. There's some caveats here, which is that the two samples are not independent. But yeah, so if M1 is equal to M2, then and if like this is independent of that, then up to this point is hopefully correct. And then this is going to be a good estimate of in general, you have to do like M1 times P hat 1 plus M2. This is going to be the pooled estimate divided by M1 plus M2, because all you form the sum of this plus the sum of that divided by the total number. So that's would be P hat. In the case where they're equal, it would be like P1. So that's under the null. That's my estimate of the shared basically probability. And then this part is not exact, but an approximation by the central limit theorem. The mean is 0, standardize the variance, and there are just differences of sums or and so if I plug this in, you can sort of argue that this is still approximately Gaussian, and so I can calculate this quantity. Okay, is it something like this familiar to people, or like just too? Have you done something like this before? No. No. Okay, it's a good attempt at the statistics. There is a bit of an issue here, which is in our case, the ZI. So we have like ZIs actually, and let me do this. We have the ZIs, which are like indicator f hat 1 not equal yi tilde, and then wi also, like it's the same sort of. It's a different function, but the same example. And then I goes from 1 to m for both. So these two are not independent because they use the same sample. I'm going to ignore this for now, right? I'm going to pretend that they are independent, but you can try to fix it. And so this variance is assuming that they are independent. Let's pretend that for now. Let's see what we get. Is the rest clear? Not clear. So let's say the example is we have, so let's say M1 is equal to M2 is equal to M is equal to 3 to 7. My P hat 1 is the risk of F hat 1, which is 0.217. I have P hat 2, which is 0.211. And I have like this shared, and like assuming that the risk is the same, the risk was going to be roughly, so what is that? If I'm not correct, So under the null, under H naught, which is saying P1 is equal to P2 is equal to P, that shared distance will be 0.2014. That's like 221.214. And then that variance, so like the standard deviation basically would be root 2 p hat 1 minus p hat divided by m. What is m? 2.7, and this is going to be 2 times that 0.214. 1 minus 0.214. In any case, you calculate this, and if my calculations are correct, this turns out to be, you can double check, turns out to be that. Okay. Oh, sorry, not that. It turns out to be 0.00331, something like that. Okay, this is saying that if I look at the difference of p hat 1 minus p hat 2, which is 0.217 minus 0.20. So what is this? This is going to be roughly 0.06. So this is the difference that I observe in the test errors, but this is saying the standard error. So how confident or how like uncertain I am is of this order. Right? It's actually there's a more zeros here. 0.06, right? 0.006, right? 0.006 is like the difference is in the third digit, but my uncertainty like is 0.03, which is much higher. Okay, so intuitively, this difference is not significant. That's the general idea that I want to convey. Okay, if you do a little calculation, you can see that your uncertainty is like 1 order of magnitude higher than the difference that you're trying to judge. Okay, so I really don't know these up to this third digit. Like I know this plus like this plus minus roughly 0.3. This is plus minus 0.3. So this could be 24 actually, like 247, or like you can see. So it's like up to this variance I have. So if you compute the difference, basically you would say this divided by that is roughly 0.187, which is like very well inside that 1.96, or this is like the 95 percentile like interval for the Gaussian, if you've seen any statistics. Like 2, like for us it's like 0.2. Let's say I would be happy if I'm in -2 and 2, okay, which is consistent. If I'm like very large, it's going to be. So do not reject the null. Okay, so rough calculation like this. It's not precise, but there's some things that we ignore, the dependency here. We can incorporate that. And then the fact that this is normal is not exactly normal, but it's a good approximation. What I want to convey is this difference here, right? The rough difference between the these two. You can try to correct for the dependence here, but is this idea sort of clear? So uncertainty in these estimates is higher than the actual difference. So the difference in the two test errors is below our like level uncertainty. So we can't really, it's best not to judge. Yes.
What do you mean by writing the plus or minus 0.03?
So that's like the variance. Let's say the variance. Oh, actually not. Yeah. So the difference is, I shouldn't do that because that's the variance of. So difference is, that's the variable. This is our, assuming that you agree with this calculation, which is a little bit iffy. This is the variant, like the standard deviation. So it's like a this is like p hat minus p hat 2 has a distribution, right? Centered around like this is 0.006. So that's the center. And then the variance is like, it's like this. right? If I go like negative 0.3 in this direction, 0.006, and then in the other direction is 0.006 plus. So that's how far you could go. If you go one standard deviation, you could like pass negative. So it could be negative or positive. So the difference is not really positive necessarily. That's what I was saying. Yeah. Yeah. So I'm not trying to like do a very like precise calculation, but this is the idea, like a statistical idea is like you can use a little bit of statistical thinking. If you really want, you can try to calculate the actual variance. See, like there's an interaction term, like covariance of Zi and Wi, because they're dependent. That would be a little bit tricky. But if you ignore that, then this gives you some rough calculation. So we really don't know at this level whether this is good or not. Like this could be like the actual risk could be higher. So we're going to stick with probably the simpler one. Okay. There's no right or wrong answer. You can use this as well. It could turn out that this is the better classifier. But if you're biased or like prefer a simpler model, there's no reason why you have to just like go through like take P class into account. And if you actually do this R part in R, it's going to output this simpler classifier. So it has some sort of a stopping rule or pruning. It's not going to do this split. So questions? Yes.
So we're using the testing errors.
Yes. The test error. Otherwise, these independents like are. It turns out that in this case, the training error is very close to the test error. You can see, but that's a different story. Okay, yeah. I just want to mention that this independence also be ignored. The dependence here. So this variance, and I'll probably assign this homework problem. It's good for you to do this variance calculation. Assumes that the two samples are independent here. Let's say this is going to be a good approximation if we did use two independent samples to calculate the test errors for these. If you really want this to be precise, more precise, like split your test into two pieces, test this on one and the other one on the other one. Then the two are independent really. And so this calculation would be correct. If you do it on the same test data, it's a little bit iffy, but it's going to be okay again in this case for the same reason that the training is actually close. But if you want to really be in the setting of this, split your test into two pieces, two independent samples, like do the test error for each classifier on one sample, and then all of this would be correct except the normal approximation, but the normal approximation is quite good. The variance would be correct in that case. Okay, sounds good. So this is like the statistics part of the course. We're going to move back more to the machine learning side, but it's just wanted to give you some flavor of some statistical ideas, how they can come in, and just whenever you're testing, you have the test error, for example, you try to compare things, just have in mind that there is a sample size in the background and there is uncertainty in these estimates. They're not like necessarily exact up to the third position here. So your uncertainty is like, in this case, much higher than the difference between these two classifiers. Okay, all good? Okay. There is this other set of things about uniform control. This part I'm going to move later. Let's see if later we might see this is the idea that tries to justify why the training error is actually close to the test error in this case. So you actually didn't need to split. Your training error would be a good sort of explanation. But because it's sort of a little bit advanced, let's like skip that for now. That concludes sort of our discussion, like an introduction to ML, like binary classifications. So all these ideas you can try to now generalize, okay? And the way that I'm going to generalize, again, one step at a time, we're going to look at what happens if I look at a continuous variable. So everything so far was for discrete variables. We saw that even if you have multiple discrete variables, you can combine them. Essentially, all the combinations of the levels would give you another discrete variable, but with many levels. And you can do everything that we did. You can do the optimal rule, you know what it is. Even in the non-binary case, like multi-class classification, you know how to do it. And then the approximation of the binary classification. So the optimal rule, we used this estimate of the regression function, which you now all show in your homework problem. This is a variant of that empirical estimate. So that's going to be our has been our estimate of, if you recall, it was like something like that. Y equal y given x equal to x is I from 1 to n. Indicator xi is equal to x. And then yi equal to y divided by I from 1 to n, xi equal to x. The reason why this looks like this, a little bit of saying what the homework is doing. So you can split it into two parts, indicator this times the indicator yi equal y. Just argue that this is like that. And then if I put 1 here, the indicator of yi equal 1 is just yi because that's a binary variable. So you end up having this binary variable. So this is the sort of our estimate of the regression function. And you know that for the misclassification rate, you just have to threshold it at 1/2. That gives you a plug-in estimate of the optimal rule. So that's how we did this. So the entire training of a classifier would boil down to calculating or estimating this regression function. And this regression function, we have a good estimate in the discrete case. The issue is, and you can also show that this looks like this, which we'll get to later. But there is an issue with this. Okay, so if I now move to a continuous random variable, as we discussed, when I have a training set of size n, with probability 1, all of the x's would be different. Okay, probability 1, they're going to be all like we will have n unique values. Let me mention here. So that's basically it. So let's suppose they have a continuous feature. By a continuous feature, I mean some feature like in R or RD whose distribution has a density, usual density that you know. And for example, x could be a multivariate normal, just a single normal variable of t is 1. So x could be like normal 0, 1, which has this density. And then x could be like uniform 0, 1. If this is like that, okay, so these are continuous variables. And if you have a continuous like model, I'm going to go draw in examples or in samples from the joint distribution. So I would have xi, yi's. And if I look at the xi part, so this is, so my training would be, remember, the training data would be x1, y1, x2, y2, ... x and yn. So this training data is not gonna, okay, so I'm gonna use, like, look at the x's. If I look at the set of all x's, these are gonna be distinct with probability 1. Okay, that's a fact of probability theory. So if you have a continuous, like technically these are continuous with the Lebesgue measure, but if they're continuous, the way that you know these is that they have continuous, or they have a density. And so whenever I draw from this, I get, every time I draw, I get a new value. And no matter how many times I draw, I'm not going to repeat for any finite n. there is zero chance that I see repeated values. And so this is what usually happens when you do real valued covariates or features as well. So if you look at your data, so I have a data set here, a new data set. This is so-called Wisconsin. This is another famous machine learning data set. Yeah, that's not right. Wisconsin breast cancer data. So there's sort of a response, let's say a diagnosis. So they have like a sample of these cells, and I think these are cells. And the diagnosis is that like it's either malignant or benign. I don't know if it's type of cancer or the cell itself, malignant or benign. And there are a bunch of covariates, like multiple covariates. I'm showing two of them here. Radius, so this is the mean radius of the cell, I guess. And this is like a measure of texture of the cell. It's like smoothness, compactness. And then the mean, I think the mean within the sample, so it's like you have tissue and there are a lot of cells, the average radius of the cells, I think. I'm not a biologist. And then there's a standard error as well. So they also have the variance basically. So I'm just showing the mean texture and mean radius, and you can see that if you look at it, there are no repeated values. Okay. For example, age is still because they usually measure it up to a year, sort of a discrete. But this is really a continuous model would be good, and there are no repeated values. Okay. Similarly, hopefully here, I'm hoping. I haven't checked, but yeah, things that are very close, but still not quite exactly the same. It could be that you find repeated values, but okay. So these continuous distributions are good models of right, continuous variables, and so if you use this estimator that we have, oh, by the way, this is also before we go that it's always good if you can like do some visualization. So if you visualize this data and plotting this as the x coordinate, this as a y coordinate. So for each row, we're going to have a point. It's called a scatter plot, x coordinate. This is going to be the y coordinate. And the color would be the diagnosis. Okay, so each one of them has like a radius and a texture, and I'm coloring it by the like the type, diagnosis. So do you think we can classify this data? Is this a good, easy classification task, hard classification? So if I just had these two features, you don't know? Is it easy, hard? Don't know. What do you guys think? Before we move on, just some intuition. Sorry? Visually, can you classify? If I didn't give you I give you the training data, and later I'm going to give you one more point, let's say, to classify. Can you decide? Yeah. How would you decide? Do what? Oh, logistic regression. Just from the plot. So let's say I'm going to give you a point. Let's say test data comes up here. How do you classify it? Yeah, malign. So malignant. If it comes here, yeah. The what?
I was going to say maybe between yours.
Right, we're gonna get to all of that. Yeah. But just visually, is it? Let's say you don't know anything about classification. If I give you this picture and give you another new point, can you classify? Yeah, this is going to be most likely benign. Yeah, what was that?
If it's on that side, on the right, then you most likely.
Right, there seems to be a side here, right? So let's say if I do like something like that, right? There are things that are limited, but I know for sure. Let's say if I do something like this, maybe I'm not sure here, but definitely seems like everything here is like malignant. There's like one point here. I'm going to be very certain that if things are here, down here, they're benign. If they're here, they're malign. So just looking at it, you see this, you can classify by I, sort of. So machine learning methods should be able to also classify. You guess that even this is called a linear classifier. So this is if this is a classifier that decides based on which side of a line you are. This is a linear classifier. A logistic regression would be like this. Even a linear classifier is going to do well. So it's always good if you have, you can do it, of course, in higher dimensions. But if you just are exploring the data, you could like plot every two features, like scattered plots of two features. You can do it. There's a homework problem. You can do it with other features in this data set and decide which one. If I'm going to pick two, which two would most likely give me a good classification. You can see there that things are quite like mixed here. So a linear classifier is not going to be able to like perfectly classify given the training. But we get into that. K-nearest neighbor is also good. We're going to get to that as well. But even if someone doesn't know anything with classification, visually, if I give you a point here, you have some intuition. So if things are here, probably it's difficult. Things are here, probably easy. Okay, sounds good. We're gonna work with just one feature even to like make it simpler. So I'm gonna stick with this, not the two-dimensional one for now. I'm just gonna see whether I can classify based on a single radius. Can I decide? Questions? So let's see if I can just apply this rule. I have this rule. Let's say xi is that radius. Radius mean. Okay. What do you think would happen if I apply this rule to that data? So if I want to classify, for example, I have this data, and then the rule is, let me show it here. So eta hat x is summation xi is equal to x, yi, I from 1 to n, divided by summation I from 1 to n. What kind of function do I get if I apply? Yes.
I don't think it would work because like these are continuous values, right? So it's very like unlikely to be exactly different. I think each of those like cells.
Right, this is good. So let's say if this little x was like 14.4, let's say there are just, these are up to like the third digit, that's it. So if x is like 14.400, what would be eta hat x? I'm gonna like encode this as let's say depending on how you want to do it. Like malign is 1, malignant is 1, benign is 0, 1. I can't do this with yeah, so this formula only works if yi's are binary. Remember that the general formula is like this. You can do it for multi-class classification here, but for this to work, yi you have to encode as 1, and then one binary basically. So 1, 0. Okay. So what would be eta hat x? Oh yeah, so suppose x is 14.400. What would be my this classifier? So this is going to output something for x. Eta hat x. What would it be? It would be 0. Why? Right. If you look at that sum, only one of these indicators would be active because no other xi is equal to x except the xi of this. So only one of these rows is like everything is 0 except for this row. And you just average the y's over that single row, which is just going to give you the y of that. And if x is like 13.010, you're going to like just look at this row and it's going to be 0. So if you think about it, what is going to happen is if this is like that, if x is equal to one of these training examples, that's just going to give you yi. If x is not within that class, x1 up to xn, then it's sort of undefined because you get 0 divided by 0. There's no example. So if you haven't seen x in your training data, you have no idea. This doesn't mean anything. If you have seen it, you're just going to do yi. Right? This is an example of an interpolating estimator. So you just exactly interpolate the training. Whatever is in your training, you're going to just output it exactly. And there's no way for this to know about examples that you haven't seen. So this works perfectly for discrete cases because there's a lot of repetition and you're getting guaranteed to have seen all the examples if you have enough samples. This came up as well. So if your data set is small, even if you have discrete cases, you might not have seen all the levels. But if you have like 2 levels for your feature and 1,000 samples, you have seen the 2 features already. And then, but this is not going to work. So that's going to be, this is going to be the estimator. There's going to be another exercise. You can show, you actually showed it. So there's going to be yi if x is equal to xi, undefined otherwise. Okay. Does that make sense to people? Is it clear? So if you just imagine what this is doing, if you remember intuitively what it's doing is it's looking at all the cases that match whose x, the feature matches x, and then averages y over those. So all, like if I pick one x, if the x is already in the training data, so there's only one of these. So I'm going to average over just one row of the corresponding y. And so I'm just going to get this, just yi. So it's sort of a useless average. And that will be your estimator. And you're going to be guaranteed that if you observe a new data point, a new sample is going to land here. Because as I mentioned, every time you sample from the distribution, you get a unique value. Okay, so you had like, you've seen 1,000 cases, you form this, now you go into the wild, you observe a new data point, 1001, and it's going to be guaranteed to be different from every other one. So it's going to be undefined. So it's a useless classifier, unless you, basically it's going to, the performance is going to matter on this part, which you haven't defined yet. Yes.
So in this case, the x side needs to be like
Needs to be
unique in the training set.
I am assuming it's unique. I'm assuming it's coming from a like a continuous distribution. So if it's coming from like a Gaussian or something like that, or something that has a density, we know with probability 1 that all of the training x's are going to be unique. Yes. Otherwise, there is some information that you'd use. Yeah. But that's my assumption. You can see this is a good example where things are going to be unique. So it's not going to be defined. So that, I'm going to point this out. An interpolating estimator or interpolation is exactly this. If you have a regression function that gives you, when you apply it to your training, it reproduces exactly the label in your training. This is interpolating. Okay, this is not necessarily bad. It says that on the training data, I'm going to give you the exact label that you have. Whether it's going to be good or not is what it does outside the training. Okay, this basically doesn't do anything, but you can define it outside the training to be doing something, and depending on how you do it, it might be a good classifier, it might be a bad classifier. It's easy to make a bad classifier. So for example, if I choose randomly, or if I choose it to be 0 always, if I choose it to be 1 always. So such an estimate can be useful if it does a sensible job of putting outside the set of training features. It's also possible that it behaves poorly. It does a poor job outside the training set. So this is going to be an exercise I'm going to assign. So you could go and show that in that exercise 2.5, the 2 exponentials, if you remember the hard example, the exercise in homework 1. You can show that with, so suppose that I define this estimator to be 0 everywhere. That's undefined. So now I have a well-defined estimator. So yi if I'm on the training, 0 if I'm outside the train. You can show that the training area is going to be 0. Okay, so you'd have an estimator that's no matter what you'd get, you'd show that the training area is always going to be 0. So perfect fit to the training data. And then you'd show that the test error or the risk, the actual generalization error is going to be a constant. And that constant is going to be bigger than 0. Again, for this estimator. Maybe you can add another point here. Maybe I'll add it. That if you, instead of being 0, you flip a coin, fair coin, and decide, the same thing would happen. Okay, if you randomly choose outside the training set, this is the risk. Or if you want generalization error, aka generalization error, aka misclassification rate in this case. Okay, so the risk is going to be something positive. The training error is always going to be 0. So this is an example where the training error does not converge to the risk. So that's why I mentioned that if you want to evaluate a classifier, you have to use an independent sample. This shows that, okay, this is an example where you're guaranteed to perfectly fit the data. So the training error is going to be 0, but no matter how many samples you gather, your risk is going to be positive. Okay. If you evaluate this over an independent sample, maybe I'll add another point here. So evaluate the estimator f hat n over a test set of size, let's say 1,000, you would get close to this constant that you evaluate. Okay, so you correctly get that the generalization error of this is not 0. It's something bad. Okay, so that's a good example to show that you could do bad with interpolation if you do something trivial or not thought of outside the interpolation regime. But it doesn't say that all the interpolating estimators are bad. Actually, there is like a trend now in machine learning to do sort of, they train like these huge neural networks that do interpolation basically, but they still do good outside the interpolation. And this is one of the things that people are really interested in trying to understand. How could you have something that interpolates the training data, but also does good outside? And there's some sort of simple ways of actually showing examples of estimators that do this interpolation, but also do good outside, so that your actual risk is also going to go down as your n goes to infinity. Okay, good. People understand? But so we have to do something else. One thing to do is like, we don't necessarily need to be interpolating. This is like a new trend. We don't have to like reproduce the training data. You could like be good on the training. You don't have, this has 0 training error. But I don't necessarily, so this is, the interpolating solutions always have 0 training error. I don't necessarily need to be 0 on the training as long as I can be small on the test. I want the training error to be small, but small enough to be close to the test error, not the generalization error, not necessarily 0. So we don't have to do interpolation. So let's now think, how can we modify this estimator? Is there a modification of this that I can do to actually get something sensible outside the training data? So let's go back to this. Like, what is your intuition of, is there a way of modifying this? So for example, this is not exactly equal to that. Like, let's say this. This is not exactly equal to that, but they're pretty close. Yeah. Right, but I don't know if that's the case, right? So you don't know if, so you already see the picture, but I haven't seen the picture. I want to sort of make a simple modification of this, right? So if you think about what this is doing, it used to average over all the examples that had the same X as our test case. Okay. We don't, in the continuous case, we don't have to be exactly the same. We can be close, right? So 14.86 and 14.87 are pretty close. Okay, it's much closer to each other than like 20.664. So is there a way that I can modify this estimator?
You want to round it up?
Sorry?
You want to round it up to say
Round, yeah. So one thing that you can do is to try to round. There's a good example. So round everything to, let's say, maybe just an integer. Then I would have a lot of repeated values and you can have. So that's good. Yeah.
I was thinking we say xi equals to x, we make xi minus x. The absolute value is less x, so it's not.
Great. Okay, that's another thing that I can do. So that's like suggestions. So what was your name?
oh, it's in there.
Can you spell it?
J-I-N-T-I-A-N.
G-I.
J-N-T-I-A-N.
Jintian. Okay. So that's Jintian's estimator. We're going to call it that because I don't know if it's a name, but you can publish it. So round, yeah, estimator, or GE for short, or J estimator, round, round, this is one, x to, let's say, the nearest. It could be to the second point, like the nearest integer. Or to like the second 2 digits or 1 decimal digit. What was your name? Okay. AK. Akshat's estimator. So what should we do?
This my condition is same x, x, but have xi minus x, and you can take the absolute value of that. Because less than certain
Replace this with xi minus x less than or equal to epsilon. Right. So your estimator would be summation I from 1 to n. Instead of the indicator of that being equal, I'm going to do this, which is a very sensible thing to do. And then I'm going to average over these indicators. So basically, you just replaced so replaced this with replaced 1 xi exactly equal with this, which is saying your epsilon close to x. And then this is the same, this was the same in the denominator, if you remember. So this is just going to select all the rows that are within, like if I have an x, for example, if I give you x, which is, let's say 13, and then epsilon is, let's say 0.5, I'm going to go look at all the xi's that are within 0.15 of, so it's going to be xi's in 12.5 and 13.5. Right, for example, this cuts it. Unfortunately, nothing else. So let's say do it 1. Say 1. Let's do it 14.5. 14. I get 13.5 and 14.5. So yeah, so I'm going to get, for example, this would be there. Right, this would be there. This would be there. Unfortunately, nothing else, right? Yeah, so at least I get like some repetition going. Now I'm going to average over these, right? And you can, if you change this epsilon, you're going to take more or less, right? So if I take it to be 1, you get more rows. So basically, this allows you to, let's say instead of averaging over exactly the same x's, pick x's that are close enough to your current test test set. So your test case is I'm going to classify a case that has X turned out to be 14. I'm going to borrow from these rows because they're close to 14. It's a very sensible thing. Rounding is doing something very similar. So if I round, then I'm going to have a lot of 14. So now I'm going to like average. So if I do, this is like Akshot's estimator. Jin Tian's estimator would do, for this 14 would do, let's say round it up or down. Let's round it down. Or like, yeah, I want to have a lot of 14s, but round down. So then you would get this and this and this and this and this. So then you average over all of these. So this would produce an estimate. Yes.
So why are we treating radius mean as like categorical variables rather than
They're not categorical.
so like the way like you're interpreting it feels categorical where it's like, oh, between these certain ranges it's one thing and then between these ranges it's another thing and there's like no, they're just independent. Yeah.
Did I do that? So if you round it, it looks like categorical a little bit, right? But the thing that I'm emphasizing here is similarity. So if you round, you get things that are similar, right? Close. If for example, you have 14, if you round it, 14 and 17 are still pretty different. And they have a different, like they're large, the distance is large. So imagine if they're numbers, the distance matters. The distance or similarity. So what I'm looking for is actually similarity. So this has some sort of a measure of similarity. So all these things that are proposed are trying to measure whether this case is similar to whatever you've done. And they're measuring similarity in terms of distance. In this sense.
Yeah, so like in the case of like 14, but then like you have like 15 or
Yes.
13, those could also be important towards the classification rather.
Yes, it could be, but yeah. So what is your suggestion? So let's see. What do you propose?
Just using logistic regression.
Why would you use a logistic regression? What is wrong with this, do you think?
Well,
Let's say you didn't know about logistic regression. If you wanted to come up with a classifier, so would you say that these two examples are closer or like more similar than, let's say, the case that has string? If the radius means something, an example that has like radius 20, right, should be like more. Is it more similar to the case that have 14 or the case that have like radius 14.4? If the radius tells you something about them, align and see. This is probably closer. So anything that we can do to like find things that are similar. Similar here is measured by the distance to, right? Sorry?
The nearest neighbor thing.
So the nearest neighbor would also do. So the nearest neighbor is another one. 3. Let's say, for example, 3 nearest neighbors. Okay. For example, if I have 14, I'm going to pick, let's say, 5 nearest neighbors. So which ones would it be? It's going to be, yeah, this is probably going to be one of them, right? This is going to be one of them. What else? Maybe this one. Let's say 3. 3 is good enough for us. Something like that. You can see it's still going to pick up sort of similar things. Maybe like 3 nearest neighbors to 14. Right? So your classification would be similar to, let's say, maybe Jin Tian. Maybe if you round actually to the nearest integer, probably it will be similar. Exactly. Right. This is the closest to 14. If you round to the nearest integer, and the 3 nearest neighbors seems to be the same. Okay. Sounds good. Any other suggestions? These are all interesting and valid classification, like classifiers. And what they're doing is like they're borrowing information from nearby examples to help you classify. So nearest neighbor is very clear. Nearest neighbor goes and finds the examples whose X is closest, so your 3 closest ones, and then average over those. Okay, so you can think of this as an example of this where you replace this with the indicator of whether xi is among the three closest members, like neighbors of x. Okay, so this is going to be similar to what we have there. It's going to be some I from 1 to n, indicator whether xi is among the three nearest neighbors of x. So that indicator, and then yi divided by the same thing, summation I from 1 to n, this entire guy, this goes there. So it just replaces that indicator with some other indicator. What kind of examples I need to choose? I'm choosing all the examples that are three nearest neighbors. Here, I'm choosing all the examples that are within epsilon of, all the examples in my training that are within epsilon of dx. Here, I'm going to choose all the examples that are going to be exactly equal to x after a round. So that you're just changing that indicator. Because we're out of time. A general idea is to, that just captures everything, is like have a similarity measure here, okay? I'm gonna define a similarity measure, it could be anything. So this measures how similar x is to xi, and I'm gonna replace the indicator. So replace 1 xi equal to x with this like soft measure of similarity. This is like hard similarity. If they're similar, if they're exactly the same. I'm gonna relax it, saying I'm gonna have a measure that tells you it's like, okay, it's like sort of similar. So once you replace it there, you get the general class of classifiers, and you can verify that all of these guys that you propose, including k-nearest neighbor, this is we'll see, this is an example that also has a name. All of these fall within this. So I'm going to call this like local averaging estimator. Okay, this class encompasses a lot of things. Okay, depending on how you define the similarity measure, these things even need not be numbers. So xi's could be images. If you can define a measure of similarity among images, then you can classify images. If they're graphs, you can define similarity among graphs. So this is going to be high if x and xi are similar, and it's going to be low if they're dissimilar. So the examples that it gave me, this k is going to be either 0 or 1. For example, they're going to be similar, and similarity would be 1 if they're within distance of epsilon of each other, otherwise it's going to be 0. For the nearest neighbor, it's all going to be the same. So x and but this is not symmetric, but x is going to be within, it's going to be similar to xi. Xi is within the three nearest neighbors of this, otherwise it's going to be 0. You can have a more gradual like decay of similarity. It doesn't have to be 0 or 1, it could be like 0.45 or 0.4. And this gives you a very general class that we're going to come back next time and explore. Okay. Sounds good? Questions? Okay. Good. See you next time.